Okay, this is continuing with chapter 6.2 notes on differential equation word problems. So let's look at example 3. It says the rate of decay of radium is proportional to the amount present at any time. If 60 milligrams of radium are present now and its half-life is 1,690 years, how much radium will be present 100 years from now? So I'm going to set up these ordered pairs. I know that time, represented by year, will be my independent variable, and radium amount is my dependent variable. So I know that 60 grams of radium is present now. So we're going to let now represent t equals 0. So 0 comma 60. Okay. And its half-life is 1,690 years. Okay. So we know that after 1690, there's going to be half of the initial amount that is available. So after 1690 years, 60 will decrease down to 30, exactly a half. Okay. And the question is asking is how much radium will be present after 100 years. So we have a couple of order pairs that we can use to help us write our specific equation. And then once we have our specific equation, then we can plug in 100 in for t and solve for r, the amount of radium after 100 years. Okay, so let's create our differential equation now. It says the rate of decay of radium. So rate of decay, you see the word rate, going to be representing some sort of a derivative. So the derivative of radium, okay, the rate of radium, so I'm going to let that represented by r prime, is proportional to the amount present at any time. So is proportional. So we know this is in the form of y equals kx, but now it's going to be proportional to the amount of radium at any time. So proportional to the amount, so k times r, r representing radium. Okay, so r prime is equal to k times r. Okay, next step, we are going to rewrite r prime as a more specific form. So dr over dt is equal to kr. Separate the variables. Let's get the r on the left, everything else on the right. So dr over r is equal to k dt. Okay. Take the integral of both sides. Once we separate the variables, we want to begin solving for r. So this is in the form of 1 over u du. So natural log of absolute value of r is equal to kt plus c. We want to solve for r, but r is stuck inside this natural log function. So to get it out, we're going to exponentiate both sides because we know e to the ln of a value, which is going to cancel out to be just that value. So r is equal to e to the kt times e to the c. And then this is a constant that we can represent by just c and pull that in front. So r is equal to ce to the kt. Okay, we have our general equation. Now we're going to use the order pairs available to us to help us solve for c and then to solve for k. Okay, so r is equal to ce to the kt. Let's solve for c first. So plug 0 in for t, 60 in for r. So 60 is equal to ce to the k times 0. We know e to the 0, which is going to be equal to 1. So we know that initial value, c, is 60. So r is equal to 60 e to the kt. Okay. Next step, we want to solve for k. So let's use the other order pair that's available to us. 1690 plugs in for t. 30 plugs in for r for radium. So 30 is equal to 60 e to the 1690k. Divide both sides by 60 because we want to take steps to eventually solve for k. So let's move the 60 over. 30 over 60 is 1/2 or 0.5. Now this e to the 1690k, we want to bring the k down from the exponent that is that's sitting there as an exponent. So we're going to take the natural log of both sides to allow us to bring that down. So natural log of 0.5 is equal to ln of e to the 1690k. 1690k can be pulled down in front because this is using a the power property of logs. And then natural log of v is simply just going to go to 1. So natural log of 0.5 is equal to 1690k. Divide both sides by 1690. So we have our k value. Okay. Now let's look at our specific equation now that we have c and k found. So r is equal to 60e to the ln of 0.5, 1690, ln 0.5 divided by 1690 times t. Okay. So now we can plug in t in for 100 in for t, and solve for r, because that's what we're looking for. After 100 years, how much radium is left, how much radium is present. So plug 100 in for t, and we simply plug all this in the calculator. Okay? And that'll come down to 57.589 milligrams. And if you have any decimals, we always round to 3 decimal places.